National Electrical Code Section 250.66 dictates the requirements for the size of the grounding electrode conductor. The specific scenario involves using ground rods as the sole grounding electrodes in a system where the service conductors are number 2 aluminum. The question revolves around whether a number 8 copper conductor is permissible for connecting to the ground rods, given that Table 250.66 might indicate a maximum size of number 8 copper based on the size of the service conductors. However, 250.66 introduces a specific provision stating that the grounding electrode conductor for grounding electrodes of a rod, pipe, or plate electrode shall not be required to be larger than number 6 copper. This doesn't imply that a smaller conductor is permissible if calculations based on Table 250.66 suggest it. Instead, it establishes a ceiling on the conductor size for rod, pipe, and plate electrodes. The key point is that 250.66 sets a minimum allowable size of number 6 copper for the grounding electrode conductor when connecting to ground rods. Even if the calculation from Table 250.66 based on the service conductor size would permit a smaller conductor, such as number 8 copper, the requirement in 250.66 overrides that, mandating the use of at least number 6 copper. The grounding electrode conductor plays a critical role in providing a low impedance path for fault current to return to the source. This path is essential for the operation of overcurrent protective devices, such as circuit breakers or fuses, during a ground fault. If the grounding electrode conductor is undersized, it can increase the impedance of the fault current path. This increased impedance can hinder the rapid clearing of the fault, potentially leading to elevated voltage on grounded metal parts, posing a shock hazard and increasing the risk of fire. Using a grounding electrode conductor smaller than the code required minimum, in this case smaller than number 6 copper for ground rods, can compromise the effectiveness of the grounding system. The code mandates the minimum size to ensure adequate capacity for safely conducting fault current. Therefore, even if calculations based solely on the service conductor size seem to allow for a smaller conductor, the stipulation in 250.66 must be followed. A number 6 copper conductor must be used to connect to the ground rods. The function of the grounding electrode conductor is to create a low impedance connection to earth. This low impedance is crucial for facilitating the flow of fault current back to the source, allowing overcurrent protection devices to operate quickly and clear the fault. An undersized grounding electrode conductor will impede this flow, potentially delaying the operation of the overcurrent device and increasing the severity of the fault. The code provides specific requirements to ensure that the grounding system is capable of handling potential fault currents. These requirements are not simply arbitrary numbers. They are based on engineering principles and practical experience, designed to minimize the risk of electrical hazards. Firstly, it is important to understand the relationship between conductor size and impedance. Smaller conductors have higher impedance than larger conductors. This means that a smaller conductor will offer more resistance to the flow of current. Secondly, consider the potential fault current levels. The amount of fault current that can flow in a system depends on several factors, including the voltage of the system, the impedance of the source, and the impedance of the fault path. In general, larger systems with higher voltages will have higher potential fault current levels. Thirdly, the purpose of the grounding electrode system is to provide a low impedance path for fault current to return to the source. This low impedance path is essential for the proper operation of overcurrent protective devices, such as circuit breakers and fuses. If the grounding electrode system has a high impedance, it can impede the flow of fault current, which can delay the operation of the overcurrent protective device and increase the risk of electrical shock or fire. Section 250.66 is very clear in its requirement, stating that the grounding electrode conductor shall not be required to be larger than number 6 copper when connected to a rod, pipe, or plate electrode. This means that even if calculations based on the service entrance conductor size would require a larger conductor, the grounding electrode conductor is not required to be larger than number 6 copper. However, it is important to note that this does not mean that a smaller conductor can be used. If the calculations based on the service entrance conductor size require a larger conductor, then that larger conductor must be used. The exception in 250.66 only applies when the calculations would require a conductor larger than number 6 copper. The code sets these minimums to guarantee a level of safety. The grounding electrode system works in conjunction with the equipment grounding system to provide a complete path for fault current. The equipment grounding system connects all of the non-current carrying metal parts of the electrical system together, such as the metal enclosures of equipment, metal conduit, and metal junction boxes. This ensures that all of these metal parts are at the same potential. If a fault occurs, such as a short circuit between a live conductor and a metal enclosure, the fault current will flow through the equipment grounding system back to the source. The grounding electrode system provides a low impedance path for this fault current to return to the source. This allows the overcurrent protective device to operate quickly and clear the fault. In addition to providing a path for fault current, the grounding electrode system also helps to stabilize the voltage of the electrical system with respect to ground. This can help to reduce the risk of electrical shock and improve the performance of sensitive electronic equipment. The grounding electrode system is an essential part of the electrical system, and it is important to ensure that it is properly installed and maintained. If the grounding electrode system is not properly installed or maintained, it can increase the risk of electrical shock, fire, and equipment damage. A grounding electrode conductor connects the grounded conductor, typically the neutral, of the electrical system to the grounding electrode. The grounding electrode is a conductive rod, plate, or other object buried in the earth that provides a connection to ground. The grounding electrode system is intended to provide a low impedance path for fault current to return to the source. This low impedance path is essential for the proper operation of overcurrent protective devices, such as circuit breakers and fuses. Without a properly sized grounding electrode conductor and grounding electrode system, fault current may not be able to return to the source quickly enough to trip the overcurrent protective device. This can result in a dangerous condition such as a fire or electrical shock. Therefore, it is essential to use a grounding electrode conductor that is sized in accordance with the NEC. The NEC provides specific requirements for the size of the grounding electrode conductor based on the size of the service entrance conductors. In general, the larger the service entrance conductors, the larger the grounding electrode conductor that is required. In a specific scenario, even if Table 250.66 might suggest a smaller size based on the service conductor's 250.66 that dictates the minimum size for connecting to ground rods. A number 6 copper conductor is the minimum acceptable size for the grounding electrode conductor in this case. The grounding electrode conductor carries fault current back to the source, allowing overcurrent devices to trip and clear the fault. An undersized conductor will impede this flow, potentially delaying the clearing of the fault and increasing the risk of electrical hazards. For the ground rods, the code stipulates a minimum size of number 6 copper. The reason for this specific requirement stems from the necessity to handle potential fault currents effectively. Ground rods, by their nature, are intended to provide a direct path to earth for dissipating fault currents, ensuring that any fault within the system is safely channeled away. The grounding electrode conductor serves as the critical link between the electrical system and the ground rods, and its size must be adequate to facilitate this process. Number 6 copper is selected as the minimum size to offer sufficient current carrying capacity and mechanical strength for the purpose. The grounding electrode conductor plays a vital role in ensuring the safety and reliability of the electrical system. It is essential to follow the NEC guidelines to ensure that the grounding electrode conductor is properly sized and installed. A grounding system with ground rods serves as a reference point for voltage stabilization. Grounding systems are designed to limit voltage from things such as lightning strikes, line surges, or unintentional contact with higher voltage lines. The connection to earth grounds the electrical system and stabilizes voltage. Voltage stabilization helps to prevent damage to electrical equipment and reduces the risk of electrical shock. The NEC provides specific requirements for the installation of ground rods. These requirements include the depth at which the ground rods must be driven, the spacing between ground rods, and the type of materials that can be used for ground rods. The general rules that one has to follow for ground rods include that they be at least 8 feet in length and driven into the ground, with at least 8 feet of contact with the soil. If rock bottom is hit, then it is permissible to bury them in a trench. The National Electrical Code provides requirements for properly bonding metallic parts of an electrical system to ensure electrical continuity and safety. The NEC guidelines are put in place to minimize electrical hazards. Bonding creates a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices such as circuit breakers or fuses to quickly trip and disconnect the circuit, reducing the risk of electric shock or fire. It also ensures that all metallic parts are at the same electrical potential, preventing voltage differences that could cause electric shock. Grounding and bonding are essential components of an electrical system, providing safety and reliability. Grounding establishes a connection to the earth, while bonding connects metallic parts together. Grounding and bonding are also designed to limit voltage from things such as lightning strikes, line surges, or unintentional contact with higher voltage lines. The connection to earth grounds the electrical system and stabilizes voltage. The National Electrical Code also specifies rules for selecting the correct size of grounding and bonding conductors. These rules are put in place to provide a path for fault current to flow back to the source so that overcurrent protective devices trip, and to also ensure the proper operation of the overcurrent protective devices. The purpose of the bonding jumpers around service equipment is to ensure a continuous electrical path between all metal enclosures and equipment, thereby maintaining a low impedance path for fault current to return to the source. The bonding jumpers provide an alternative path for fault current, bypassing any potential points of high resistance or discontinuity, such as loose connections or corroded surfaces. The goal is to create a reliable and effective path for fault current to flow, enabling overcurrent protective devices to quickly trip and disconnect the circuit in the event of a fault. Bonding of metal water piping is a key aspect of electrical safety, as it helps to maintain a low impedance path for fault current to flow back to the source. By bonding metal water piping, any stray voltage or fault current can be safely conducted back to the electrical system's grounding point, reducing the risk of electric shock or fire.